So, in this lecture, first I will discuss one example problem when foundation is resting on slope, and then I will discuss about the another case when the foundation is resting on layered soil. Okay. So, let me discuss first the example problem when the foundation is resting on a slope, that your one foundation which is on the slope. So, here it is on the surface of the slope. Okay. So, beta value is given 20 degree, but here the eta is 0 degree, because it is not the inclined base, but the foundation is on the surface of the slope, and the width of the foundation is say 2 meter, and the distance from the slope edge to the foundation edge is 1 meter. Okay. Height of the slope h is 6 meter. So, what are the properties are given? C is equal to 0, phi value is given 40 degree, and beta angle is 20 degree, unit weight is 19 kilonewton per meter cube, and df is equal to 0. But remember that df can be certain value also, and I have discussed how you can use those chart by using df. Okay. So, now first I will use the Meharov equation, and then I will go for the Henson and basic. So, Meharov the n q for C equal to 0, q u ultimate load is half gamma b n gamma. Okay. Now, b by small b by capital B, small b is equal to 1, capital B is equal to 2. Okay. So, small b is equal to 1, capital B is equal to 2, this value is 0.5. Now, df by b is equal to 0. Okay. So, now we have to go for the chart. So, that chart, this is the chart. So, that chart as your C is equal to 0, only phi, and phi is 40 degree. So, b by b is equal to 0.5. So, 0.5 means it will be somewhere here. Okay. So, this is 0.5, and your phi value is equal to 40 degree, and df by b equal to 0, that means firm line. So, phi is equal to 40 degree means firm line, and so, and this is your beta value is 20 degree. So, that means this is the line. Okay. So, this is the line. So, if I extend this line, so it will here, and remember that in the chart in few cases they are normal scale, and few cases they are log scale. So, when you taking the values from the chart, you keep in mind it is not normal scale, it is sometimes log scale also. So, a log scale, you know that how the values are represented. So, based on that you have to pick the value. So, similar to here, it is a log scale. Okay. You can see that 100 to 200 difference is more compared to 100, 200 to 300, then 300 to 400, and so on. So, here, so this is the value. So, this is, it is 40. Okay. So, that means your n gamma q is 40. If there is it is a cohesive slope, then you have to use this chart. Okay. Remember that. And as I mentioned that if your width is greater than or less than or equal to height of the slope, then how you can use this chart. Okay. So, these I have already discussed. So, now it is your these values are df equal to 0. So, corresponding your n gamma q is equal to 40. Okay. So, q u will be half into 19 into 2 into 40. So, it is 760 kilonewton per meter square, and remember that this is a strip footing. And one reason that why this equation is developed for steep footing also, and no such recommendations are given that if there is a rectangular footing what to do, because in most of the cases as is a slope, it is itself a plane strain condition. That means the slope, say length will be very high compared to the width. So it is expected that the foundation that we will place, that will also continue along the slope. Okay. So that is why it is also a steep footing kind of foundation, where the length is much longer compared to the width of the foundation. That is why it is originally developed for the steep footing. But as I mentioned, that if your case it is a rectangular footing or square footing, and you have other conditions or loading conditions like inclined load, or then the soil compressibility and all the other factors, if it is present, then you have to use those factors here with some caution, because originally it is developed for the steep footing. Okay. So now Hansen theory is now if I use the Hansen, then your QU as it is on the surface. So the second term will be 0, as C is equal to 0. So first term will be 0, only the second term will present, and then you know that equation gamma B. So here I can write N gamma, then S gamma, then D gamma, I gamma, then C gamma, say compressibility, then G gamma, then B gamma. So all the 6 factors are written, but here, so let me write one by one what will be the S gamma, because your it is steep footing, S gamma will be 1, then D gamma, because it is on the surface, so D gamma will also be 1. Then your I gamma, it is not inclined loading, so I gamma will be also 1. Then CC, compressibility, those values are not available, so we assume it is the rigid one. Even the phi is 40 degrees, so definitely it will be a general shear failure. So I gamma will be IC gamma will be 1. Then your it is not tilting base, so your B gamma will be also 1. So only you have to calculate the your G gamma. So that G gamma for as per Hansen, which is the ground factor on the sloping ground. So that is 1 minus 0.5 into tan beta to the power 5. Okay. So you can write 1 minus 0.5 into tan beta is 20 degree to the power 5. So this is 0.366. So I can write this is half. So all these values are 1. So I am not writing them. So in 19 into 2 into n for phi equal to 0. Now this case of phi equal to 40 degree, as per Hansen, the n gamma value is equal to 79.5. That I will put here, that 79.5, and it is 0.366. So it is 553 kilonewton per meter square. Okay. So now I will go for the third approach, which is basic. And again, if we have in the sloping ground, here the your recommendation you can put those recommendation, if it is eccentric loading, if it is compressibility is there, your shape factor you can provide. If remember that if it is eccentric loading, again you have to, for as per Hansen, whether it is parallel to L or B, all these issues that I have discussed you have to apply here. If your footing is that kind and loading is that kind, because here I have taken the simplest one, the steep footing, vertical load, no horizontal load. So just to show you how we can incorporate that sloping ground effect. So okay, if your different problem, as per that you have to apply those factors and you will get the value. So as per basic, that similar expression, this is, I am not writing the coefficient, those are 1, because I have already explained. So, this is half gamma b n gamma, and here g gamma will be there. Now, for phi equal to 40 degree as per basic, the n gamma is 109.4 and g gamma is 1 minus tan beta to the power square as per basic. So, it is 1 minus tan 20 degree to the power square. So, 0.405. So, this is half into 19 into 2 into 109.4 into 0.405. So, this is 842 kilonewton per meter square. So, this way you can calculate the bearing capacity by using different approach, Mayerhof, Hansen, basic. Okay. So, now the in comparison of all the methods, as that when you use which approach, that is the question. Okay. I have discussed the several approaches. I have discussed the Tazaki, Skempton, Mayerhof, then Hansen, basic and IS code approach. So, all the approaches I have discussed. Now, you have to use which approach. Now, the Tazaki, that can be applicable. Remember that when df by b less than equal to 1, but the Hansen, basic and the Skempton. So, these approaches you can use even for df by b greater than equal to 1 also. Okay. So, even Mayerhof approach also you can use. But so, that means the Tazaki can be applicable when df by b less than equal to 1, and it can be used for footing with no moment, no horizontal force, the foundation is not tilted and foundation is not on the sloping ground. Okay. So, that means the simple case you can use the Tazaki's bearing capacity equation. You cannot use the for this condition. If there is a movement, you cannot use. If there is a horizontal load, you cannot use that. If the foundation is tilted, you cannot. If foundation is on the sloping ground, you cannot. Even the foundation is placed at a depth greater than b width of the foundation, then also you cannot use the Tazaki's bearing capacity equation. In general, the Mayerhof, Hansen and basic, these three equations can be used more or less for all purposes. Okay. These are, and that is why these three equations are very commonly used or famous, because they can be used for all the more or less all the cases, except Mayerhof equation you cannot use if there is a tilting based condition, because that is not recommended. Otherwise, the Mayerhof has suggested for sloping ground and all the other cases also, inclined footing, if there is a movement, and then you can use that. Okay. So, that means the Mayerhof, basic and Hansen you can use for all the condition. Even you can use for this basic Hansen equations if df by b greater than equal to 1 also. Okay. And you can use for tilted base, foundation and sloping ground, as I mentioned. And the Skempton equation you can use for clayey soil, and it is valid for any depth of df by b. So, that means the Skempton is for the clayey soil. So, now so that means you cannot say which equation I should use always. No, there is no such condition, the which one you use always, because it is depending upon your requirement. Okay. Suppose you but in general, Mayerhof, Hansen, basic can be applicable for more or less all the cases, but Skempton is only applicable for clayey soil, and in my next design problems I will prefer to use Skempton if the soil is clayey soil. Okay. So, and then if your foundation base is within the width, you can go for the Tazika for simple condition, but it's a different loading condition or the moment or other conditions is there, you cannot use the Tazakis. So, depending upon your requirement, you have to select which one you will use, and as I mentioned that Mayerhof, Hansen, basic, all these equations can be applicable. And now, the question is when I will use these equations, that also will use these equations. That also depends your availability of the your loading and the other condition. For example, in Mayerhof, only the loading direction, only the loading angle with vertical axis is sufficient to calculate. Okay, but in case of Henson and basic it is not. Okay, because in Henson and basic you should know whether the loading is parallel to H or loading is horizontal load is parallel to B or parallel to L, because those information you should know to use your Henson. Suppose you do not have those informations available, you have the information only the angle is given, so then you go for the Mehrhof. But if you have those information, that means you know the horizontal load is parallel to H or parallel to B, then you can go for any equations, Henson and basic. So, that is why depending upon your requirement and availability of your of the values and the conditions, you have to choose soil conditions, you have to choose the appropriate bearing capacity equation. But in my recommendation that you always use the two equations, any of the two methods always, and then consider the minimum one or the lowest one as your bearing capacity value. So, always it is better to use two equations. Okay. So, now the next topic that I will start is the bearing capacity of foundation on layered soil. So, in our foundation engineering problem, generally in the foundation engineering course, we prefer to use the weighted average value for the your layered soil case, and you can consider those properties for that for particular one layer, and then I will get the bearing capacity of the soil. But now, if the soil is on the layered soil and there are different cases. So, basically in this case I will discuss the two layered soil case only. That means, either the sand is resting on clay or clay is resting on clay or the sand. So, that means, I discuss the three cases or even four cases you can see. That means, the sand, then sand clay and clay clay, and there is another case I will discuss in later on. So, first I will provide that we have a layered soil case where that this is my ground surface, this is the ground surface and you have a foundation here. This is the foundation and this is the ground surface. Okay. So, this is the ground surface and you have a foundation where the foundation is QU and the width of the foundation is B. Suppose this is the width of the foundation and this is the center line of the foundation. Okay. Now, we have two layers. This is my layer 1 and this is layer 2. And in this particular case, the first case I will discuss, there is always your first layer is stronger and the second layer is weaker. In the next case, I will discuss the second layer is stronger and the first layer is weaker. But the first case, I will discuss that always this first layer is the stronger layer stronger soil and this one is the weaker soil. Okay. So, what will happen? So, as your lower layer is weaker, now if this is your depth of foundation df and this h is the thickness of the stronger layer below foundation. Okay. Now, if the H value is very high, so that means all the foundation failure zone will be on the stronger layer. So, there will be no effect on the weaker layer. So, you have to calculate the bearing capacity as if the foundation is resting on that stronger layer and you will get the values as per the equations or the procedure that I have discussed by using different approaches. Okay. So, that means, you will get if the H value is very high, that means, the influence zone is not going to the weaker layer. But if H value is not high, okay, and your influence load is going to the weaker layer. So that means as the second layer is weaker layer, so that means what will happen? Your actual failure will occur in the second layer. Okay, so now the failure surface, if I draw the failure surface, so this is the probable shape of the failure surface as proposed by the, because these theories are proposed by originally Meyerhoff 1972 and then it is further modified by Meyerhoff and Hanna 1978. So, it is proposed that this is our possible failure surface. Okay, so, this is in the first layer, stronger layer. Remember that if the H value is not very large, if H value is small, so that the second layer will be influence. And this is the failure surface. Okay. So, this is the probable failure surface in this case. So, as if the stronger layer, the soil is basically going down, foundation is going down and it is punching basically. So, there will be a punching type of shear failure in the stronger layer, because your weaker layer will fail, which is very low strength layer. So, that means total system will try to sink. Okay. So, that is why this type of failure surface is proposed. So, now here the stronger layer, this is unit weight, phi value and the C value. This is phi 1, C 1 and gamma 1, and weaker layer gamma 2, phi 2 and C 2. Gamma, phi, C are the unit weight, friction angle and cohesion respectively. So, now how it can be calculated? Now, it is assumed there will be a straight. So, these actual failure surface is assumed as a straight failure surface now for the calculation purpose. So, that means now your failure surface is perfectly straight. Now, the dotted line, say assume that this is the dotted line, but the form one is the actual failure surface, but we assume that, or it is assumed by these researchers that you consider it is a straight line. So, now when this foundation will move along this dotted line, because now this foundation will move along the dotted line and the soil will also move along the dotted lines. Okay, so, this portion of the soil within the dotted lines, that will deform or move along, and this is the movement is along the dotted lines. So, what will happen that there will be, if there is a cohesion, so there will be a shear resistance that will act in upward direction. So, there is a shear resistance, so that will act in upward direction. Okay. So, that shear resistance we have to calculate. Now, again when this soil will try to move, as if you see the original failure line. So, the soil is moving in outer direction, obviously the soil will move in the outer direction. So, that means there will be a passive resistance that the soil outside this failure zone will give, because your soil is try to push in the outer side, two sides of the foundation. Okay, so, soil is try to push in the two sides of the foundation. So, those soils will give you a passive resistance. Okay, so, that passive resistance is say P p. So, and that will act at an angle of delta. Now, I am considering delta, later on I will change it. So, this is P p and that will act in the both the direction. So, at an angle of delta vertical to the surface, and surface is your this dotted line, you make a vertical line, and with that vertical line it is making an angle delta, because that is the case and it is common for your earthquake theories. So, if you read the earthquake theories, you know that this will act at an angle of delta. So, what is delta? Delta is the friction angle between the soil and any other object. Okay, but here this angle basically along that dotted line. So, it is soil versus soil, because later on I will modify that. and now it is considered as a delta. Okay. Now, how I will calculate the QU? So, QU will be your QB plus Ca into H. Ca into H is what? H is the thickness of this soil below the foundation. So, your cohesion will act along the H. So, that means Ca into H will give you the resistance due to cohesion or shear stress due to cohesion, and due to passive one also there will be value, because your it is in delta. So, it has two components. So, now this is your delta angle, your PP is acting. So, it has two components. Okay. So, one is your, if this is the PP which is acting, so there will be one vertical component, there will be one horizontal component. So, this angle is delta, means this angle is also delta. So, this is your PP cos delta and this is your PP sin delta. So, that PP sin delta will act in the horizontal direction, vertical direction. So, that PP sin delta, this cohesion part and the bearing capacity that this base foundation is given will be equal to the total load that is coming on the foundation, or the total load carrying capacity of the foundation, that is QU. Okay. So, this is Ca and then this PP sin delta term, and this will act in both the sides. So, right side as well as the left side. So, that is why I have to multiply with 2. Okay. So, this is the Ca into H and this is the PP. So, it is, we have to express them in per width of the foundation and then minus gamma 1 H. Now, why this minus gamma 1 H QB? I am just explaining that. So, now your QB is the bearing capacity of the base soil. Okay. So, that means from where I am this foundation is getting resistance, that as I mentioned the failure will be on the weaker soil. So, that means this weaker soil will give you the resistance, and that will get this weaker soil QB I will get by using the normal bearing capacity equation. Okay. Because now the failure, if you look at this failure surface, because in weaker soil this is the failure surface. Okay. So, now that can be your depending upon the type of soil, that can be your local shear failure also, but the failure will be on the failure second surface. So, that means that way I can get the resistance by the bearing capacity of the second layer. So, that is the bearing capacity of the second layer that we will get from the second layer weaker soil, and that I can use our normal bearing capacity equations. Okay, I will explain that how I can use calculate the QB. So, I will get the QB second layer bearing capacity plus the resistance this soil is getting because of its movement along the dotted lines. So, that one is cohesion part and this is the friction part. So, if the cohesion is present, then Ca into H is the total thickness, then the passive resistance that soil is getting, in that is the vertical component into 2, because it is acting two sides, then that will be equal to the QB. Okay, that the total, what are the vertical, basically I am taking the all the vertical components. Okay, that means QB will be equal to QU will be equal to QB plus this resistance. Now, one thing is why this gamma 1 H is used. So, gamma 1 H is used because it is assumed is weaker soil. If you assume the weaker soil is sea soil, that means in weaker soil your phi 2 is equal to 0. You assume that if for the time being I am assuming that my weaker soil is the cohesive soil. Okay? So, phi 0 equal to 0. So, now when you calculate the QB, when you calculate say the QB, how I calculate that? That QB will give me the equation that for suppose for the if phi is equal to 0, for QB expression will be what? CNC 2. Okay. Then it is the strip footing. Originally, let us first discuss this for strip footing. So, the S is your S is strip footing, the SC part is equal to 1 and inclination is not given, IC part is also 1. And then because these depth factors are already taken care, because your this depth, along this depth already these resistance, all these are considered. So, that depth factor also you need to apply. So, it will be CNC2 plus gamma df plus h, and your for phi equal to 0, your n gamma is equal to 0, nq equal to 1. So, it is 1. Because in the second layer, weaker layer, what is the thickness of the soil or the surcharge? Because second layer is due to the surcharge, that is Q. So, second layer is basically the second term is basically Q N Q. So, NQ is equal to 1, Q is equal to gamma df plus h. So, this is the QB part. Now, this way I can calculate the QB, but if you see that gamma df plus h. So, now this h part we are basically taking twice. How I am saying that? Because when I calculating the bearing capacity, I am taking gamma df plus h. So, that the gamma plus gamma into h, that surcharge contribution I am taking, as well as the same time when I taking the resistance along the soil, this part, here also I am taking the h. df part I am not taking any time. So, that I can calculate within the gamma QB term. But the thickness of this thickness part I am already been taken during the resistance calculating around the this dotted line, because it is Ca into h. So, that h is already been taken, the h part contribution is already been taken. Now, if I take again, it is during the QB calculation. So, it is maybe we are basically taking twice the contribution, one in the as a surcharge to calculate the QB, and as resistance calculation along the dotted line. So, it is recommended that the contribution we should take at least only one time. Okay. So, that is why these gamma 1 because this is also gamma 1, because the gamma 1 and df by h, because this is in the first layer. So, that is why it is recommended that you just subtract gamma 1 h, because we have taken already this h term into this resistance calculation. So, it is recommended to neglect the h term when you calculate the bearing capacity for the bottom layer. And this is that is why this gamma 1 h basically we are neglecting. Now, if you take that QB minus gamma 1 h, so that will be basically CNC2 plus gamma 1 df. So, we are basically neglecting this h contribution when you calculate the QB. Okay. So, that is the reason why I am putting gamma 1 h. Now, one thing that if during QB calculation, if you itself neglect that value and you calculate only that CNC into gamma 1 df, then no need to take minus gamma 1 H, because either you calculate QB considering DF and H, then you have to subtract that H contribution. But if you during calculation, if you take QB is only the DF contribution, then no need to subtract it. So, either you subtract it considering the total for during QB calculation, or you just do not need to subtract if you do not consider the H contribution during QB your QB contribution. So, one way, do not subtract twice. That means, once you are subtracting during QB contribution calculation, and then again you are subtracting by using this equation. No, either you subtract in this equation, in that case you have to consider H during the QB calculation, or you consider only the DF contribution, do not consider the H contribution during QB calculation, then no need to subtract this value. Clear? Okay. So, in the next class I will I will complete the full derivation, then I will solve a few example problems. Thank you.